I want to get at something that people kind of struggle with sometimes. And sometimes people ask about how f big G and f little g could relate to each other. And I want to point out that if I have f big G, I know that that's g m1 m2 over r squared. F little g is the special case when you're at the surface of the Earth. So I'll just call it m2 times ag, where that's the little mass. I know that if I'm on the Earth, we got the mass of the Earth called m1, and we might have like an object sitting on the surface of the Earth. We'll call that the m2. So if you're on the surface of the Earth, those two values should actually be equal to each other because we're a distance r away from the surface of the Earth. And assuming that mass 2 isn't enormous, its height's going to be negligible, right? So like the r value isn't going to be impacted really by the height of the object. So fair enough, I should be able to set f big G equal to f little g in the special case where I'm sitting on the surface of the Earth. Well, if that's the case, g times mass 1 times mass 2 divided by r squared is going to be equal to mass 2 times ag. And I say, well, wait a minute. Look, the m2's disappear because I could cancel both sides m2's. Gone. That means that I actually could calculate ag as being g times mass of the planet over r squared. That's one way to approach this. In other words, if I knew the mass of Mars and I knew the average planetary radius, remember, most planets are oblate spheroids, but the average planet radius, I could figure out what the gravitational field intensity would be on the surface of Mars. That's kind of cool. I don't even have to go to Mars to know that. Another thing that it means is that if I had gone around and dropped a bunch of stuff on Earth and figured out what the average acceleration due to gravity is on Earth, I could rearrange this equation and I could get mass 1, which is the Earth, equals ag divided by g times the radius squared. That means that now that I know that g value, I could go around dropping stuff on Earth and figure out what the ag value is just by dropping things and watching how it accelerates. And if I knew the radius of the Earth, I could use this Cavendish result to figure out the mass of our planet while I'm standing on my planet. And that's actually what Cavendish wanted to do. He described his own experiment as weighing the Earth because his goal, nobody had done it before, was to figure out what the mass of our planet was while you were on the Earth. And that's a pretty big deal, okay? So we can play around with this equation when you're on the surface of the Earth to figure out what the gravitational field intensity is going to be on the surface of the Earth. We can play around with this equation to figure out what the mass of a planet is if you know what the other values are. This is a nice special case outcome of setting f big G equal to f little g. Okay? Now sometimes people will do something like this. They'll say, well, if I'm at the surface of the Earth, how would the force due to gravity compare to when I'm 3 times farther away from the center of the Earth? Don't you figure we could use this equation to do something like that? And a popular thing that people do with that is set it up as a ratio. They'll say fg1 divided by fg2 equals g m1 m2 over r squared. And actually, I shouldn't even say fg1 fg2, I should say fg initial, fg final, if I was going to go from an initial position to a final position, divided by g m1 m2 over r squared, where this would be the I initial and this would be the I final. And what you notice with that, if I'm comparing two forces as a ratio, notice that a whole bunch of stuff cancels out. And if I carry that through to completion, what I end up saying is that, and maybe I'll throw a post-it note down here. If I simplify that out, that's 1 over r initial squared divided by 1 over r final squared, which is the same as saying 1 over r initial squared times r final squared over 1. In other words, the ratio of fg initial divided by fg final would be equal to r final squared divided by r initial squared. And so there's this nice cute little way to compare the forces between two different locations, and this would be sort of the pattern of thinking for doing that. Okay, so I wanted to put out a few ideas because it's something that might show up in homework that you would find helpful. Okay?